So, welcome everyone. It's really a pleasure having you all here, and it's even more a pleasure to welcome our guest, Professor Basil Hiley, today. It's a great honor for us to have him here today, especially as he opens up the first talk of our new Wigner lecture series. This will be the first talk today, so it's a great pleasure for us. Before I hand over to him, let me quickly give you a short biography. So, Professor Hiley was in '61 assistant lecturer at Birkbeck College, University of London. In '62, he received his PhD at King's College on the topic of condensed matter physics. In '95, he was appointed chair professor in physics at Birkbeck College. In 2012, he received the Majorana Prize in the category Best Person in Physics. Also, of course, you all know Professor Hiley also that he was a long-term co-worker of Professor David Bohm. And among their many achievements was the book The Undivided Universe, an ontological interpretation of quantum theory, which is now considered one of the major references in quantum theory. Some of you might wonder what the relation is to our institute. We have the pleasure to host the Wigner initiative at our institute, which is rooted here. And Professor Hiley strongly supports us, and this also gives kind of the stage for today's talk. And with this, I kindly ask Professor Hiley to start.
Right.
Thank you.
Thank you very much. First of all, I ought to say that this particular talk was not aimed at the Wigner Institute. It was something that I was very interested in, and you kindly published a paper of mine,
Yes.
which was more geared to that particular side. And this is just background material, so that one can see how it fits together. Because as you say, my main interest was in quantum mechanics, trying to understand quantum mechanics. And in fact, I was out with my son walking the other day, and he said, "Dad, do you understand quantum mechanics now?" And I said, "Sorry, I'm still struggling with it." Anyway, so that tells you that it's not an open and closed book at the moment. And so what I wanted to do with this is to actually show how the Bohm theory, which is usually thought to be something way out, is actually in the centre of the general algebraic approach, and it comes out as a particular example of this general algebraic approach, of which Wigner was one of the starting points. And in fact, the interesting thing was that many years ago I saw the Wigner's paper, his famous 1932 paper, where he just slaps down his Wigner function, and then he's a little asterisk and says, "I want to thank Szilard for pointing this out." And it always amazed me what Szilard had to do with this distribution function. About 5 years ago I learned that the reason why he put that in there was not because Szilard had given him the idea, it was because he wanted to get Szilard a job. And so he thought a reference in a phys-rev paper would probably go down well with his... now whether this is true or not, I think it's actually written somewhere, but I can't remember whereabouts it was written. Anyway, so this is really trying to fit in several different approaches to quantum mechanics, showing they're one and the same thing. I always begin this because this was Murray Gell-Mann who got a Nobel Prize for physics. And even in 1980 there, this talk he gave, quantum mechanics, that mysterious, confusing discipline which none of us really understand, which we know how to use. It works perfectly, as far as we can tell, in describing physical reality, but it is a counterintuitive discipline, as social scientists would say. Quantum mechanics is not a theory, but rather a framework from which we believe the correct theory must fit. That was 1980. I think it still applies now, but there are things that are coming up in there which still we feel very uncomfortable with as physicists. So please let me tell you, I'm talking as a physicist with a mathematical interest. Okay, with that background then, the aim of this talk is essentially the following. Why is the mathematical structure of quantum mechanics with its Hilbert space operators, and why is it so different from classical mechanics? Is it because the behaviour of matter is really that different? Or could it be that the maths is not so different? In other words, you can see coming together in this both classical physics and quantum physics as a limiting case of one for the other rather than entirely different. So I'm not going to be interested in interpretations, I'm going to be interested in the mathematics in this particular tool. Right. So, in classical mechanics, we all play billiards or snooker or whatever, and we have a very good intuitive feel of what's going on. And we have a phase space in which positional momentum is well defined, and if we're any good with the snooker cue, we know how it all works. In quantum mechanics, you don't have position and momentum. You replace them by operators, whatever that means. They're called observables, but in fact you don't observe those, you observe eigenvalues. And then what you have is these operators are acting on wave functions, either in the X space or in the P space, but never both together. This is the standard approach. And this led George Mackey, who very good mathematical foundations of quantum mechanics, very eminent man. Since a point in phase space has no physical meaning, notice what he's saying, neither does the notion of a probability measure in phase space. And this, for me, leads to the doctrine of the primacy of configuration space. I think we should be working in phase space. And the reason I put on the title, Seeing the Impossible Made Possible, is to show that this is that George is wrong here. And I essentially want to show how we use phase space, and that's where the Wigner distribution comes in, and where we see the relation between classical physics and quantum mechanics are related mathematically. Okay, so let me just first of all very quickly go through the similarities and differences between quantum mechanics and classical physics. Well, I think this was very appealing to me. Over here we've got our x and p. Over here we've got some operator function of x and p. No, we either use psi of x or phi of p. We don't use them both together. Nevertheless, when we're doing classical physics, we have the equations of time development using the Poisson bracket. Quantum mechanics uses the commutator bracket. Here's the Poisson bracket defined, commutator defined there, and we have here the peak with a Poisson bracket defining delta function. Over there, for the first time, you see second time, you see h bar coming in with a delta function. Then, if you use the very simple Hamiltonian, you find here classical physics. You get with the Poisson brackets, you get the Hamilton's equations of motion. When you look in terms of the operators, you get the Heisenberg equations of motion. You see, the structure is essentially the same, except one's the algebraic structure is the same, but we represent it in a different space. Now, finally, I just want to add this Hamilton-Jacobi theory. This is the Hamilton-Jacobi equation, and this is where Schrödinger actually started searching for quantum mechanics. And what I'm going to show is that there is an equation which looks like this, and this is actually in the classical limit, that particular equation, Hamilton-Jacobi equation. So what have we done? Well, what we've done is, rather than using the algebras per se, what we've done is to develop a representation. So what we've been looking at in the way physicists work is they're always looking at representation. So they either have a representation in X space or in P space, and that is what I call the doctrine of configuration space. That you never look at it in terms of phase space. Okay. Now, surprise number one. I've got a series of surprises I come across in this work. Having contradicted George saying you can't do, George Mackey saying you can't do this, let's now forget about the uncertainty principle. Let's forget about it just for a minute. Play the game with me. And then let's have a look at a translation in X space. And so we can write our translation in the following way. Then let's have a look at a translation in P space. Okay, we write it down with, and now you see we have the operators coming in, but they're as essentially Taylor expansions. So they're not really operators as such. so just a taper expansion. And then if you follow Weil and write take the exponential alpha p out of there, the exponential alpha x out of here, and introduce these two quantities, u and v of alpha, then what you find is that if you've got x and p satisfying the Heisenberg relationship, you actually get a relation between these two, showing that you're in the middle of a non-commutative algebra. So you've already got to a non-commutative algebra, and you really haven't mentioned quantum mechanics at all. And it turns out, I mean, I don't know how many people realise it, but the people who study radar know more about the Heisenberg group, that is the group which follows from the generated from the Heisenberg algebra. They use the Heisenberg group day in, day out. And radar theory has got nothing to do with quantum mechanics. It has to do with waves, but not quantum mechanics per se. Okay, so one of the things I always felt was that once we had the Heisenberg algebra, we're into quantum mechanics. We're not. We're into an aspect of mathematics which is not yet quantum mechanics. Okay, now what von Neumann did was actually to say, let's actually combine these two generators into one exponential. And that turns out to be an element of the Heisenberg group. So generate the Heisenberg group with it. And what the group the alpha, where are the alpha and beta? What are these alphas and betas? The way von Neumann does it, he doesn't say what they are, he just calls them alpha and beta. And what he shows is they actually span a symplectic space. And we know that in classical physics, we have this invariant, a two-form invariant, which defines the symplectic structure. So we've got the symplectic structure here in both cases. And the interesting thing is, what is the relation between alpha and beta and P and Q? Well, Neumann left them open. And what happened then was, let me say, now what von Neumann did next was to say, okay, can I find a mapping from my operator space onto a space of functions in this symplectic space? Ordinary C infinity functions in this symplectic space. And what he showed was that you can actually expand any operator in terms of these functions here, alpha and this S of P, and this alpha was called a symbol. Now there it looks very abstract. And if you compare this with the usual approach, there's what we do is we take our elements into the configuration space and formed transition probability amplitudes, getting the special case of where probability comes into quantum mechanics. But what happens if we use not the complex number, but we turn these bracket notations the other way around? What we've got here is an element of the algebra, and in fact it's a density operator. So that one starts with a density operator, one can also get mixed states in here as well. So the idea is that we don't worry about the wave function, we go to the algebra, the algebraic description of the state, which is in terms of the density matrix. And then we find the expectation value is just the trace of rho times A. And now if we form this object here, taking the trace of the function S that von Neumann introduced over this density operator, what you find is you have the expectation value of an operator, which is in terms of the symbol, which is that these are functions in the alpha beta space, times what looks like a probability distribution. This is the big probability distribution. The trouble is, when you look at the details of this probability distribution, you find it takes negative values in the very place where quantum mechanics shows its ugly head. And so this, for a long time, this negative probabilities was, this all came out just at the end of World War II, you'll notice. And Moyal was working on this under the direction of Bartlett, who was a statistician at Cambridge. And he was very much for what Moyal was doing, and argued that there is nothing wrong with having negative probability measures. That was his claim. And Dirac also joined him in that. But of course, Modern theory says the probability measure must always be positive definite. Being a physicist, I say, look, don't worry about that. We're dealing with a non-commutative symplectic manifold, not a commutative symplectic manifold. So maybe things are different when you're dealing with non-commutative geometry, essentially. So this is where this modern things about non-commutative geometry come out. And then you've got this question of, can you have non-commutative probability theory, and what does it mean? Okay, I'm not going to go into that discussion at the moment. Okay, so now wait a minute, we've got C infinity functions on alpha and beta, but where there is there's something must be not quite right. Where does the non-commutativity come in? Well, what von Neumann did was to say, all right, I know that in the operator form A and B don't necessarily commute, but what is the relation between the symbols C, A and B of the operator? Those should have small c, small a and small b. Okay, so then C infinity functions on this this space, alpha beta space. And then what von Neumann showed, notice this was 1931, 10 years before the Moyal paper. And what he shows was that this product is actually written in this particular form here, and this is now called the Moyal product, except von Neumann discovered it in 1931. And if you look at Moyal's paper and von Neumann's paper side by side, they are isomorphic. That always leaves me with the worry, did Moyal know that, or did he invent it? I think he invented it independently because he was looking at generalizing a statistical theory which had non-commutative aspects to it. And in fact, what Moyal did was simply choose alpha equals x and beta equals p. And of course, then you immediately say, well, wait a minute, George Mackey said you can't do that, because you're not supposed to know what x and p are simultaneously. So what's going on? Okay. Yeah, that's okay. Now then, how can we understand this? There seems to be some contradiction between the results we're getting here and what George Mackey said. Well, what David Bohm and I did way back, I don't think we're very famous for this, but I think it's one of the best things we ever did. We were talking with Herbert Froelich, who was at Liverpool University, and he was very interested in superconductivity and superfluidity. And he said, if I want to discuss superfluidity, I want to take my density matrix, but I want to make it, and I want to make it a function of 2 points in configuration space. In other words, this is not a local theory, this is a theory which depends, it's a bilocal theory, if you want. Depends upon 2 points in configuration space. And what you can do is, if you write it like that, is what we expect, but then do the Fourier transform. And now simply transform coordinates. Let us choose a new set of coordinates that we have a mean value x, which is the sum of the two divided by 2, a difference, and we do the same in momentum space. If we now put that in this expression here, we find we get a density matrix of cap x and tau. And when we work all this out, we find that the object we get here is identical to the object that's treated as a probability measure in the Moyal case. But notice, it is a direct transformation of the density matrix. And that's why it has negative values, because there's no condition on a density matrix having to be positive definite. Okay, so what this means, in my way of looking at it, is that the alpha and beta should not be identified with the x and p of a particle, but should be identified with the mean value of some cell in phase space. So where quantum mechanics comes in is that you cannot localize an object in phase space. but nevertheless you can, with these symbols, describe this behaviour. And then we've got things like, well, does this mean... Remember, all the time I'm talking about a single particle. You often find people, when they're dealing with the Wigner function, immediately go into many particle systems. And then you sort of lose track of what's going on in the morass of particles involved. I'm talking about a single particle. So what does it mean for a single particle to have 2 points associated with it simultaneously? So the suggestion is that it's a quantum blob. That's my friend Maurice de Gosselin calls it a quantum blob. This is where non-locality in quantum mechanics actually starts from. Is there a new topology involved in this non-commutative structure? And then of course there's always, I don't know how many people know about the Gromov no-squeezing theorem. It's a very interesting theorem which actually comes from classical mechanics. And for me, it's the harbinger of the quantum uncertainty principle. Let me explain why. Remember, in classical physics, when you're dealing with symplectic geometry, you always have Liouville's theorem, which says if you take an area or volume of phase space and you use any diffeomorphism, you can spread it out into a thin, thread-like thing all over phase space, as long as the volume remains the same. Gromov showed that if you restrict yourselves to symplectomorphisms, that is, symplectomorphism is a morphism which keeps its canonical transformation. It keeps Hamilton's equations of motion invariant. Then you can never squeeze volumes of dx, dpx. You can take dy and dx, you can squeeze that if you like, but you cannot squeeze the complementary variables in the quantum mechanical sense. And this is known as the symplectic camel. And it actually doesn't go back to Maurice de Gosselin, but there's a very nice article in American Journal of Physics, if anybody's interested in it. It actually goes back to the Russian mathematician Arnold, who actually coined the idea of the symplectic camel. You see, the idea is that if it's Liouville's theorem under a general diffeomorphism, make it into a thread and you can thread it into a needle. But if you only allow symplectomorphisms, you've got your head stuck and the rest doesn't follow. And that's classical physics, nothing to do with quantum physics. Nothing to do with quantum physics, that's classical physics. Okay, and in fact this invariant is now known as a symplectic capacity, and for me it is a footprint of the uncertainty principle. What quantum mechanics adds is that there is a minimal cell structure, and that's where h bar comes in. You can't squeeze that below h bar by any means at all. Okay. Now what I've done there is look at the early days von Neumann, where he was looking at the algebraic structure of quantum mechanics without using Hilbert space. I want to emphasize that. For me it was a surprise to find it there, because as a physicist I'm always brought up on mathematical foundations of quantum mechanics by von Neumann, and it's all Hilbert space. This 1931 paper of von Neumann's has got no Hilbert space in it at all. It's purely algebraic structure that he's looking at. And of course that leads on to the Murray von Neumann algebras that the mathematicians are very fond of playing around with. Okay, so we've seen the Heisenberg equation of motion. But where the hell does the Schrödinger equation come from? I'm sorry, I'm hesitating here because I think it's a very important question, because everybody thinks Schrödinger's equation, we're off. But where the hell does it come from? How does it fit into the general structure? If you look at somebody like Feynman, please, great respect. It came from nowhere. It came out of the mind of Schrödinger. That's not very helpful. What Schrödinger was looking at, he realized that there was a relation between geometric optics, that's where you do ray tracing with your lenses, and wave optics. And what Hamilton had showed is that the ray optics is an exact analogue of classical mechanics. And you can actually write down the rays in terms of Heisenberg's equations of motion with suitable transformations. Everything works beautifully. And what Schrödinger was asking is, I don't know how to pronounce it, undulatory mechanics. Now, this was written in German, I don't know whether it was translated properly or not, but he's looking for some sort of wave mechanics. And unfortunately, he did not know all this stuff about the symplectic geometry which has been uncovered in the last 30 years. Now, so how does this story all fit in with a modern idea of symplectic geometry? Well, what we find is that if we're looking at ray optics or Hamiltonian dynamics, we're using the symplectic group on a symplectic manifold. This is all classical physics I'm talking about here. And what you can do if you want to get to wave optics, it's ray optics, you want to get to wave optics, you lift it into the covering group. And the covering group of the symplectic group, the linear part of it is the metaplectic group. It's more complicated than this, but just let's take the linear part. It's the metaplectic group, and that is where the wave properties are actually sitting. So they're not independent of the classical, it's in a deeper, I'm calling it deeper structure, higher structure, I don't quite know, the covering group. What you find is then, that if you look at the mathematics, you find that you've got your symplectomorphisms, this stage where it takes one distribution into another distribution by a symplectic morphism, Fess is a symplectomorphism. Now the interesting thing is if you lift this onto the covering group, you then find Schrödinger's equation appearing in there. In other words, Schrödinger's equation is a one-parameter subgroup in the metaplectic group. So it's not completely isolated from anything else. It's actually embedded in the mathematical structure if you bother to take the covering group. And I think this is very significant because if you're doing spinning quantum mechanics, what you find there is to get spinning, you've got to lift from the ordinary rotational manifold with the rotational group on, you've got to lift it up into the double cover. And if you lift it up into the double cover, you find spin. So it seems as if quantum mechanics, in a way, is living in the double covers. And that's so that it's not now something totally different. It's just you're not looking deeply enough at the structure. Okay, let's go on. Now, what has all this got to do with the Wigner function, which is what we're supposed to be talking about here? Well, let's go back to phase space, and then remember we got this result out by von Neumann, and this I've taken the inverse Fourier transformation of the density matrix here, or the density operator, I want to call it. And then if we do inverse Fourier transforms on this, we suddenly find that this f of x and p is actually the Wigner function. So the Wigner function is coming out of a blob in phase space. And that's why I now link the Moyal approach with Wigner, and I call it the Wigner-Moyal, and I think lots of other people do it as well. But this is the way I look at it and the way I see it coming out as part of one big structure. Okay, now let's have a little bit closer look. Tell me when you're fed up. Because I can stop at any minute now. Okay, let's have a closer look at this non-commutative structure, and I'm calling it the Moyal algebra, but it's really the von Neumann Moyal algebra because they're isomorphic to each other. And someone once said, well, von Neumann gets so much credit for everything, call it the Moyal. Don't give him any more credit, he deserves it. Anyway, so what do we say? Let's now form two types. Because we've got non-commutativity, order of operations is very important. So let's try to put it together in terms of a difference between the order and a sum. And this is known as the Moyal bracket, and this is known as the Baker bracket, which doesn't get such a big song and dance talked about it, but the Moyal bracket does. Okay. Now, what does the Moyal bracket do? Well, what Moyal showed was that although you've got that abstract definition for the star product that von Neumann produced, you can actually write it in a rather more interesting form where you've got derivatives, this acts on A, that acts on B, this acts on B, and that acts on A. And it's an exponential. And it's very easy to show that you get x star p minus p star x equals I h bar. So you've got the non-commutativity in there, but not in the Hilbert space. It's in the phase space. Okay, so then if you, the Moyal bracket, if you put this in the Moyal bracket, you find it's the sine. If you put the Baker bracket in, you find it's the cosine of that exponential. So you're looking at those. So you're looking at the real and imaginary parts of the whole thing. And now the important point about these equations is that if you take the Moyal bracket and go to the order h bar squared, you find you get the Poisson bracket out. And well, it looks innocuous here. If you go to the Baker bracket, it does tell you that everything is going to be commutative, provided you're not looking at order greater than h bar squared. In other words, you've got classical physics already in this mathematical structure, sitting there if you neglect these things. Okay, now what about the dynamics? So we want to know how this distribution behaves with time, and therefore, because of non-commutativity, we've now got to put the time development operator multiplying on the from the left and from the right. And we also have to do the time operator in there. Notice this little trick I've done here. So that when you add and subtract, you get the Moyal bracket equation here, which just happens to be the classical Liouville theorem in the limit of order h bar squared. And much more intriguing is the Baker bracket equation, because that's the one I pointed out that I was going to tell you about on the second transparency. The Baker bracket is the sum of these two, and you've got here not a derivative, but an antiderivative. I called it it's not an antiderivative, but it had a minus sign in there, and it wasn't a derivation. If it's got a minus sign in there, it's not a derivation. What? I mustn't swear, must I? Because I'm on camera. What the hell does that mean? Well, what I learned to do with David Bohm was whenever you're in trouble, always write the wave function in terms of its real and imaginary parts. Put it in the equation. Here, by the way, is the... that's just shorthand for the minus sign. It still doesn't look like anything. But then what I decided to do was to go to the limit, h bar squared, and what you find in the limit, h bar squared, is the Hamilton Jacobi equation. And that's where Schrödinger started. So if Schrödinger had been able to actually deduce his equation, he would have had to have known all about this non-commutative structure. But fortunately, he just guessed it, and thankful for him. But this is how it all sits together. So for me, the real structure is in this non-commutative algebra here. Now I want to bring together this Moyal Wigner work together with Bohm's work, because it's always said, well, Bohm's got nothing to do with this, surely. You know, particles moving along trajectories have nothing to do with this. And I get surprise number 2. I was sitting on a boring 3-hour train journey with Moyal's paper, and I thought there's got to be something related to Bohm's work in this Moyal paper. Remember, Moyal was 49, Bohm was 52. And I happened to get as far as the appendix, because 3 hours is a long time, and we do get to the appendix eventually, even for a long time. And what I saw was that what Moyal does, because he's treating everything as a probability distribution and not worrying about negative probabilities, he asks the question, what is the conditional expectation value of the momentum given that you're assuming this is a probability distribution in 2 random variables? And what he showed was it can be written like that. Well, actually, if you now do, as I recommended, as David Bohm always recommended me to do, write its real and imaginary parts, And you find that that momentum is exactly the Bohm momentum. So the Bohm momentum comes out as a conditional expectation value of the Wigner distribution. Now, the second point is, Moyal actually asked about the transport equation for this, and he used Heisenberg's equation of motion. And I can't go through the details, but what he found was that you get this equation out, and that is identical to the Bohm equation using the quantum potential. Because if that term is zero, what's left here is just the classical Hamilton-Jacobi equation. So just by simply splitting these two, looking for the conditional expectation values, you actually arrive at the Bohm theory straight away. And I call this the quantum Hamilton-Jacobi equation because it has the Hamilton-Jacobi form and it has this extra term in it. And it's this extra term that I'm actually working with this group of experimenters to see if we can find some numbers to put to this so that it's not just something which comes out of the formalism, but it's actually something we can point at in the experiment. Okay, and I should say if you want all the details are all in my reference there. Okay, so now we can fill in the Bohm phase space. But this equation is identical to that equation, this is identical to that. Here we've got one more, the Moyal momentum. And of course, if you've got the v by dt is equal to grad s, what you can do is you can integrate it. And if you integrate it, you get this beautiful picture, which is essentially the interference fringes that you get from two slits. If you're using electrons, you get this picture here. And this is something which Bohr said was impossible. And in fact, John Bell, in one of his classic papers, says he saw the impossible done. And that was that calculation. Here's the fringes, you see. But you'll notice something strange about them. Here's the two slits, here's the string. There's nothing here at all. Why are the billiard balls, if they are billiard balls, electrons, why are they moving like that? Well, all you've got to do is to work out the quantum potential. And then you find that here are the two slits in the background, and if the trajectory, I'll call it a trajectory, if the trajectory is along the plateau there, it's a straight line. But as soon as it hits the potential, which suddenly dips, it comes back up again, the rate of change of the potential gives you the force. And so you get the thing dashed across like that. Okay, there are more of these. You can do we had a session once where everything that we used the Bohm theory to show you could replace all the mysterious collapses of wave functions, etc., using this theory. Penetration through the barrier, AB effects, the whole lot can be fitted into this particular story. And it was, well, not quite generally ignored, but in the early days we were shown the door. Can't do this, nothing to do with quantum mechanics. Okay. Then surprise number 3, if I might bring it in. About 4 or 5 years, 4 years ago, this particular diagram appeared in Science. And you notice that it's not too far removed from that. Not quite the same, but you know, it's for an experiment, it seems to be moving in the right ballpark. And what he did was to find that if you look at these, if you try to measure the Ponting vector, you find that the energy, you can get energy flow lines defined out. This is experiments, not theory. This is experiments with a single photon going into a two-slit setup. Now the only trouble with this is you've got a sort of very interesting question. What do you mean by a Ponting vector for a single photon? Didn't think the photon had a position in the momentum. And therefore there was a whole problem here. And in fact what you've got to do is to go to field theory. I'm not going in that direction here. what we reach is, can you do the same thing now, not with photons, but with non-relativistic particles? And that's what I'm doing with a group of experimentalists at UCL at the very moment. We've got one group using excited helium. We've got another group using excited argon. We're almost there. I would love to say, here it is. We're almost there, but we only started a year ago. And even the Germans let us down. We got a telephone. We ordered some pumps from them. Very sorry, you're going to be a month's delay in delivery. Why? Power cuts in Germany. Is this true? Or is it? Yes, this is not acceptable. Sorry, that was okay. Now surprise number 4. I'm sorry, I said this was full of surprises. I was being badgered by one of the guys around me saying, why don't you look at Lagrangian theory and what you're doing? That's a load of rubbish. But in the end I succumbed and I said, okay, let's look, because those previous photons were measuring the Poynting vector is essentially a component of the energy momentum tensor. So now let's see, can we say anything about the energy momentum tensor for a particle in the Brownian spirit? Okay. Well, what you do is if you use standard Euler-Lagrange theory, you get 2 equations. One gives you the Schrödinger equation, the other one gives you the complex conjugate of the Schrödinger equation. And now if you humour me, we can look at this as with the arrows on, because I want to compare it with the arrows that I've been using previously. You've got left translations and right translations, and in quantum mechanics you have to distinguish between left translations and right translations. That's the message that comes out of this. Now then, what you find is, if you then use the Euler-Lagrange equation, convert it into the real variables, you get the 2 equations here. That's the Liouville equation, and that's the quantum Hamilton-Jacobi equation. And what you find there, have I got it on there? The central part of the Bohm equations again. Now then, let's have a look at the energy momentum I've looked at the energy momentum tensor, and because we're doing Lagrangian theory, this is standard form, you can write it down like that. And then if you work out T0 mu, lo and behold, you find it's actually the Bohm momentum and the Bohm energy. So that the conditional expectation value turns out to be the 4th component of the energy momentum tensor. And that is something physical. It's about energy. It's about the movement of energy. And what is more insignificant, when you look at the Bohm theory in particular, all you ever see is it's done in non-relativistic domain. By using the algebraic approach, you can actually generalize the whole thing to deal with Pauli spin and the relativistic Dirac equation. So when you hear people saying, oh, you can't do the relativistic theory in the Bohm, you just say, no, you can. And what you do there is you use the orthogonal Clifford algebra. And remember, I talked about the covering group. And the Clifford algebra is the way you discuss the covering group. And the metaplectic group stuff is really the symplectic Clifford algebra. Okay, now then, so why have physicists neglected all this? They neglected it all because they refused to take the quantum Hamilton-Jacobi seriously, because that's just a conservation of energy. They felt they couldn't conserve energy. So what they do instead is they say the momentum of the particle is the integral of this over all space. In other words, they're looking at global property rather than local properties. And what the Bohm theory is doing is looking at local properties, and what quantum field theory is doing is looking at global properties. And there's an interesting debate developing, the question. Remember what I said here was I'm dealing with a single particle, but I was describing it with 2 positions in configuration space. And this is sort of the thing that's reflected. What the hell is a particle when we're talking about quantum mechanics? So it's not much about Wigner here, is that all right? Yes. That just suddenly dawned on me that, where's Wigner? The Wigner is in the algebra itself, the Wigner function is embedded in the algebra itself. So it's all part of the whole story. It's not something completely different. This is what worries me about when you say the Wigner initiative. I know what you're using it for, but remember, no, shush, no, let's get on with this. I'll talk to you after. Suddenly a thought came into my mind. No, I'm sorry, I'm on surprise number 5. And that was that Aronoff and Weidman came up with this strange idea of weak values. And what is a weak value? Well, a weak value is where you take your operator. I'm in Hilbert space now. Forget the algebraic structure at the moment. I'm in Hilbert space. Aronoff, I've just heard him speak this morning. He's always in Hilbert space, and he gets into a mess. But don't tell him that yet. Right. So normally, look, you've got this funny thing here. Because if psi and phi happen to be orthogonal, that's going to be 0 underneath there. So this weak value can blow up to infinity. And this worries the physicists. It doesn't worry me. Because notice I haven't said anything about labeling values in this. Okay. Now then, how do they appear in the formalism? Well, it's very simple. If you're looking at expectation value, and then you can jiggle the formulae around until you actually find the weak value here, and then Aronoff said, oh, this is the pre-selected value, this is the post-selected value, and there's a big song and dance about that. Whereas in fact what you do, first of all, it's a value, but it's a complex number. But if you look at the real part, and this is where the surprise comes in, it's nothing more or less than the bone momentum. So his weak value happens to turn out to be just the bone momentum, and it's just the energy force component in the momentum tensor. And you get the same for the Bohm energy. So everything, it's just the Bohm theory again. They're measuring variables of the Bohm theory. They say they're doing something completely different. It's a bit like Monty. Do you guys haven't watched Monty Python's Circus? Yeah? Now for something completely different. Remember, anyway. Okay. So when you look at weak values when P is involved, what you find is that not only is there a momentum here, there is also an imaginary part of it. It turns out to be the osmotic momentum. In other words, as if there is some kind of, the particle is embedded in some kind of quantum fluid, and it's undergoing stochastic processes. And the imaginary part is the osmotic. This is what Nelson actually introduced. And then what you find is that the Bohm momentum, as I said, is just the weak values of momentum, and the imaginary part just happens to be the osmotic momentum. Now, the other thing that turns out is if you work out the weak value of the kinetic energy, you find not only does it keep the Bohm momentum, but it also adds this quantum potential. And that's where, in the group that I'm working with, we are trying to actually pinpoint the quantum potential, because it's actually something which occurs in this expression. So if we can measure this and we can measure that, we can therefore measure Q. Okay, now that might be more. Do you want to know? You don't want to know how to do it. It's reflected internal and external. Okay, and here is the experimental setup. Here is the Gaussian wave packet which comes in a single photon. You pass it, they call it a weak measurement, it's got nothing to do with measurement. You pass it through a calcium crystal which splits the vertical and horizontal polarization, makes one go faster than the other. And then when it comes out the other side, as long as the wave packets of the two have not completely disappeared, if they overlap, you actually get a change in phase which you can measure, and it's that change in phase which actually enables you to construct those trajectories. I just went through that quickly, hoping, and this is the way you do it. I'm sure you're not interested in that. Okay, I just want to do one final thing. What about working entirely in the Dirac theory? Well, we can go through putting the density operator in terms of two variables like that again. And then what we find is, this is something mainly for physicists. Right? I just want to put it out because something very interesting which worried me for a long time, and that was that in the Clifford algebra, I could always find idempotence in the algebra because it was a non-nilpotent algebra. And that enabled me to do all the Dirac theory. When I was looking at the symplectic structure, which should be the symplectic Clifford algebra, I couldn't find a idempotent in the algebra because it's nilpotent, and if it's a nilpotent algebra, it doesn't contain any idempotence. And this seemed to me to be odd. And then one day I was looking at Dirac again for about the 600th time, and I happened to have the right addition, because if you look at the first two additions, he doesn't mention this. And that is that he actually removes this line and puts everything in the algebra. So what Dirac was actually doing was algebraic quantum mechanics, not Hilbert-space quantum mechanics, but he was showing how it could be related to Hilbert-space quantum mechanics. And there you actually put all the information that's in the wave function, you put it inside the algebra in terms of the left and right ideals. And then what he did was he called this thing the standard Kep. And if you put two of those together, it's just the idempotent, which is exactly what I needed in order to balance the whole thing up and make the whole thing work properly. So that the algebra we should be dealing with in quantum mechanics has that extra addition in there. And it turns out the physicists have smuggled it in, sleight of hand. You find on paper that it's a very classic paper in Roosevelt in physics. He has the projection onto the vacuum, which it just pulls it in without saying where it comes from. It's just this thing here. Okay, so that's... Then finally, we look at the left and right development of the algebra. We get these two equations again, continuity equation. And now we get this new... I thought this was a new equation, actually, because we've got this funny antiderivative, and it's equal to the anticommutator bracket. And I thought, oh, we've got something new at long last, but unfortunately the chemists already been there beforehand, and they don't put it in this form, but they essentially got it in there, saying that not only do you need the Poisson brackets for describe, so if you're using Wigner function anywhere, you're only using the Poisson brackets. There's the other bracket, the Baker bracket, that has to be brought in order to get a complete description of the whole thing. And this, okay, so now we've completed this picture, and there we've got the quantum algebra on the configuration space. And now, how do we get from the configuration space to the bone momentum, etc.? Well, you simply project the algebra into a particular representation. Remember when I said what we're doing in quantum mechanics is putting things in the representation, and forgetting about the fact that there's a big algebra underlying the whole thing. Now we've got the algebraic structure set up, and if we want to find a representation, then we can use these projection operators here. This projection up into X space, and we get the continuity equation, and we get the quantum Hamilton-Jacobi equation, but there's more. In the Moyal distribution, remember I had the probability distribution was X and P, and Moyal formed P bar. You can also form X bar. So you've got two pictures coming out of this. And one actually corresponds to the X representation, the other one corresponds to the P representation. And now what we've got here, instead of, where is it? Oh, it's not there. Instead of grad S, P equal grad S, X is equal to minus dsP by dt. So we can now have here not only in configuration space but also in momentum space. So that means you can have trajectories constructed out of a phase space constructed out of P bar and X, or P and X bar. And this is what people with the Wigner function do. There's a paper, I'm sorry, this is a scrappy slide which really needs filling out. I didn't have time to do it. But they actually project the Wigner function into the momentum representation and the position representation. And that's exactly what we're doing here. So that we're in the same ballpark and we're using a different language. It's nicely done in that physics today. If anybody's really interested in that aspect of it, I recommend it. Now I want to just, good, just right. Last slide, I want to talk about the philosophy. Because what we've got here are two different images. The X image and the P image. And they don't agree with each other. You can't transform one into each other. You've got to do a whole homomorphism. So what the hell does this mean? And this is where David Bohm came in. He said there's a much deeper structure which gives rise to the non-commutative phase space. Namely, in this particular, if you've ever got non-commutivity, you can never display everything in exactly the same picture. This is where essentially what Bohr was talking about when he was talking about complementary principles. But this is a much more direct complementary principle, and you see what I'm trying to do with that illustration with the lady. In there, you've got two images represented. You can either look at the old lady or the young lady. And I'm just wondering, how many people saw the old lady first? Oh good, I'm not alone. Desperately searching for the young lady again. Okay, but this sort of is a metaphor for the implicate-explicate order that David was very interested in. Then what you find here is the Moy algebra. What I claim is that the Moy algebra shows you that the X space, that when you do this transformation, from the X to the P, you're actually hologramming the whole space. So that the X, every point in X space is hologrammed into a little bit to every point in P space and vice versa. It's got nothing to do with uncertainty principle. We just interpreted an uncertainty principle, but it's actually changing the whole structure that underlies quantum mechanics. And what this means is that quantum processes are not going on in space and time. And this really roasts me, if you like. That's my claim. It's not going on in space and time. It's going on in a hidden way. This is not hidden variables in the sense of the old-fashioned hidden variables. It's really saying that we've got an implicate order which is described by the functions, the non-commutative functions, but we can only project out explicate manifolds. And we can't project them out altogether, just like the old lady, young lady. They cannot be all put on one picture. So we cannot stand outside of physics and say, like God saying, oh look, that is what is going on. We're actually involved in the all. And we see these shadow manifolds, what I call, it's not shadow manifolds, I think there was a Polish mathematician who called them shadow manifolds, and I thought that was a good idea. And then the classical world emerges when you actually find non-commutivity. When you find commutivity, and the two pictures come out to be the same. So that's my conclusion. So this shows you how the algebraic structure actually, the classical world emerges from the quantum world and not the other way around. And one of the big problems is people always try to start with the classical world and put in quantum mechanics. Well, you asked me to talk.
You did.
I don't know what you make of that, but thank you for listening.
Thank you. All right, some questions.
In the last slide, you said that you need to start from the quantum and go to classical, but in a couple of your sort of analogies where you're talking about SO3 going to SU2 and all this. And
the symmetry groups are independent of whether you're in classical or quantum. That stays the same whether you're in quantum or classical.
But then you also talked about generalizing from classical to quantum. Right?
No, it's starting with the quantum. In other words, you've got to start with the covering groups, the simply connected groups, not the doubly connected groups.
But as you show with sort of this star products, which I think you can also show just with expectation values and Taylor expansion H, that the first term is the Poisson brackets.
That's right, yeah.
And the rest you just toss out when you go to classical mechanics.
Yeah,
So
that's
same
it.
as
Yeah,
zero.
yeah.
So why would you expect any deeper connection between classical and quantum since you explicitly know you've tossed out some terms?
The question is, what are the meaning of the terms you've tossed out?
Yeah.
You see, the way we have it at the moment, if you just have the Hilbert space formalism and the classical Hamiltonian dynamics, what the hell's the connection between? They look like, chalk and cheese.
Yeah.
Whereas here, at least, you see that when you can neglect the quantum of action, in other words, in the particular quantum Hamilton-Jacobi equation, I have a very nice example, because I always wondered, the examples I present are always with quantum potential fixed in time, steady state and so on, because they're so much easier to do. So I thought, well, what happens if I can make the quantum potential change in time? In fact, what I did was I was looking at somebody was doing the inflationary scenario. Remember there was the inflationary cosmos that everybody was getting very excited. I don't know whether you do, but getting very excited about. And what they did was to have a rapid expansion so that you get this uniform distribution. Okay, what they modeled it on, which is more important from my point of view, is an upside down harmonic potential. So what I said was, suppose I start with a small Gaussian wave packet, quantum mechanically described at the top of the potential, and then just let the particle drop. What you find is the kinetic energy gets bigger and bigger and bigger until the quantum potential is negligible. And you can actually show a smooth curve from the quantum trajectory into the classical trajectory. I thought that shook me, that you can actually make this continuous transformation. It actually came about because I was talking about this in Prague, and one physicist said, well, he sort of didn't like the idea of a particle following the trajectory. He said, well, how do you know it's not a green giant or something? I thought, what the hell is he talking about? And I suddenly realized I didn't have a story of a continuous transition from the quantum to the classical. That's what made me look at the upside down harmonic oscillator. So what you're doing is you're making something bigger in order not to see the quantum effects.
So it's not continuous to do like a path integral?
You can do this in terms of path integrals as well, but we actually use, to get these trajectories, we use the Feynman solution for the two-slit experiment using path integrals. We use this propagator. We're not, how can I put it? We're not doing anything here which will give you different experimental results, yet. And I'm always hoping that if we really fully understand what this algebraic non-commutative geometry is telling us, we're going to start asking questions of the physics. But my life's a failure. I have not got a critical... Except the weak, but even the weak values, that was really Aronoff who kicked that one off.
I don't remember much about that, but that's where you have the post-selection and the retro.
Yeah. But that's all language. It's transition probability amplitudes. Follow Feynman. Feynman had it dead right. How do you get a transition probability amplitude from this to this? And that's his poster pre-selection. You just keep fancy names to it.
All right, maybe, yes, please.
My question is a bit on the side of what you have presented. So occasionally in the literature one also comes about a space-time Wigner function, where this distribution, say, depends on both phase space variables and then on two time-like variables. Does this somehow fit into your picture? Or
yes, because I have done the non-relativistic side of things, and I've only talked about mean value of x and mean value of position. You can also double up the time, and I do have a paper published in a collection of papers on time, where you do have two times, and you have a mean time and a time difference. So you have a moment and a sort of universal time. Interesting. I don't know where it's going to lead. It's just you're right.
My next question is there a clear advantage of such a space-time Wigner distribution, or can it describe additional
Well, the way I
features?
tried to describe it was that while you stay within Hilbert space, you don't get any time changes at all. I mean, Hilbert space, all you're ever doing is redescribing exactly the same system. This is where the collapse of the wave function comes in. But what you can show is that you can get transformations, Bogoliubov transformations, which take you to an inequivalent Hilbert space. And the proposal, and it's only a proposal, is that real time goes from one inequivalent Hilbert space to another. And that's where the time evolution takes place. But it needs working on. So, maybe there's something in the, looking at it from the Wigner point of view, that might be very illuminating.
All right. Maybe another question? Good. Okay then. Thank you very much. I really appreciate it.
Good. I hope, not that you appreciate it, I hope it's been useful.
Oh, absolutely.
And amusing, if not.
No. Absolutely. Thank you again. Thank you.
Well, I should really say thank you for inviting me.
Oh, it's our very pleasure.
I would rather talk than sit and listen, as I said earlier.
Yes, actually. No.
Okay.